Welcome to my first tutorial in Houdini. In this episode, I really want to show how to implement genetic algorithms using the new PDG and top networks in Houdini. But before we can do this, I will give you a brief overview of how genetic algorithms work, and we will implement it in SOPs first, because that will give us a sense how much easier it is in PDG. What problem are we trying to solve with genetic algorithms? Genetic algorithms are pretty good in finding parameters that end up optimizing a particular problem. And I think the example that I would want to use is as follows. I would like to take a cube, and find a geometry that ends up minimizing the surface area while maintaining the volume of this geometry. And the way that this is going to look like is that we will sort of slowly approximate a sphere that has the same volume but that has minimal surface area. And the only thing that we will be doing with genetic algorithms here is to essentially give it a target function, which is going to be maintain the volume but minimize the surface. So let's see how we can do this. And let me explain a little bit about genetic algorithms first. All right, let's talk about genetic algorithms. In our particular case, we want to turn basically a square, sort of like so, and we want to somehow find an algorithm that finds a shape that sort of minimizes the surface, or in the 2D case, the perimeter, while maintaining the area. This sort of looks like so. How do we end up doing this? So the way that genetic algorithms work, we sort of start out with the population. This may be even just a few. This is our population. And each entry here is a chromosome that consists of different genes. Chromosome. And each of them is like a bunch of different genes that may sort of be expressed with different values. Sort of like so. And they get randomly generated. And then we want to check how well they are doing. And so basically what we end up doing is we calculate the fitness for each of these solutions. Calculate fitness, and clearly I have not much experience with the tablet. And let's say that the first chromosome is instead of 5, maybe a 6, a 3, 2, and a 4. And the fitness basically calculates how close we are to the solution that we want. And in this particular case, this may be maintain area, but minimize the perimeter, or volume versus surface. So then once we have calculated the fitness, then we end up doing a selection of the fittest, the top half. And in our particular examples, this would be the entry with the 6, the 5, and the 4. And then we do something that is called crossover. And the crossover basically calculates new chromosomes based on the fittest ones. And here we might want to combine the 6 and the 5. And we somehow mix them up. And then end up generating a new chromosome based on that. And in our particular example, we have been saying we have the square. So let's take a look at how this might be. For this example, sort of draw our circle, and then imagine that one of our chromosomes, maybe the one that fit the best, this one here, perhaps this at a point here, at a point there, and maybe another point here, and then a point here. So it sort of, fit the circle shape quite well, didn't quite maintain the area. And then here we have another one, maybe like so. Oops, not quite a circle. Maybe like so. And perhaps this one wasn't quite as good. Oops. Perhaps this one had an expression here. And perhaps then one of them was in here. And perhaps the other one was sort of an outlier. And then we had another outlier here. And then for crossover, we basically determine how many of these we want to keep. And, perhaps we randomly keep this one here. And perhaps we keep this one here. And this means that we take this one and this one. And then we end up combining them into an expression that looks like so. So we have the point over here. Then we have another point over here. And then we keep this point over there. And then we have the outlier over here. And this is now the next generation. So this was what we call crossover. And then we have another step that is called mutation. Mutation. And let's take a look at how this might look like. So we calculated our new generation here, and then with a random chance we may be changing some of these genes. Maybe we end up changing this one and sort of randomly move it, and let's say, perhaps we're moving it over here, and then after mutation, this chromosome really has this shape. And then basically after we have done mutation here, all of these chromosomes sort of get backfilled into our population here. And then we calculate fitness again. And then we pick the top examples, run crossover and mutation. And this then forms our next generation. And as we do this over and over, and we sort of always pick just the fittest ones, the hope is that over time we will actually end up approaching, our perfect solution. So perhaps, the first generation is, sort of something really crazy, and then the next generation, perhaps we have something that is sort of slightly better, and then, assuming that we actually have more genes, then, after a few generations, we have actually done something that sort of ends up looking like a circle. And that is basically it. And now let's figure out how we can actually do this all in Houdini. All right, let's start implementing genetic algorithms in Houdini. Let's put down a geometry node and start with a box. We want this to be a mesh with a reasonable number of subdivisions. And since this is genetic algorithms, we need to have multiple of these. Each of these is going to be one chromosome. So let's maybe start with 10. We won't be able to see any of these. Let's make sure that each of them gets its own group. These are primitive groups now, but we do need them as point groups. So let's do that as well. Houdini makes that very easy. Let's just the trick with this now is that we need to throw this into a solver. so that we can keep state. I like to keep my solvers red. And at this point we might actually already put in a tweak for how many chromosomes we want. So let's say num chromosomes, number of chromosomes, and let's keep them at 10 for now, but copy that parameter up here so that we can keep track of that. Alright, great. As I had mentioned, with genetic algorithms we need a fitness function, and since we are trying to turn a square into a circle or a box into a sphere, let's look at what we might want to measure. So the idea is that we want to look at the volume, which is 1, and then find a geometry that has the same volume but a much smaller surface area. So let's put the volume into the detail. Then let's also measure the area. Same kind of process throughout total area. And now we somehow want to figure out how we can sort of randomly modify this box geometry to turn it into something with the same volume but much less surface area. Alright, this is probably good to keep. Let's copy it and let's dive into the solver. Let's keep this on the side. And the usual progress here is that we put a switch in there where we keep the previous frame only if we already have some kind of solution. So on the first frame we'll keep the input, and otherwise we take the previous frame. Alright. So let's assume we already have something to work with. And for that we want to then look at each of these boxes in turn, because right now, if you remember, we have 10 boxes. So let's put a for loop in here for each number. Oops, I always do this. And that for loop should really only do this for the number of chromosomes that we have. So we still have the child levels in there, 10. And then for each of the ones we want to isolate them, we can do this with the blast node. And basically what we are blasting here is everything but the current thing that we are working on. And the current iteration we can get, we actually have to tell it that the start value is 0. What we want is the iteration value, and that comes from the for each count. And if you look on this here, you will see that it has an iteration number. This is exactly the one that we want to pull in here. And then delete everything but the stuff that's not selected. And now you see that we capped the first box. And now this is basically the thing that computes the fitness for us for each of these boxes. And the fitness function we just put in here. And it's not happy. Why? Because we didn't cache it yet. Alright. So now if you look at this, we have 2 of our attributes, which are 6 for the surface area and the volume is 1. And now we somehow want to turn this into the fitness that we want to measure. Right. Let's put an attribute wrangle down here. So we get to write some vecs, and I like to make these black. And what is it that we want? We want an area score, and we want a volume score, and then we somehow want to compute a total score, and for the sake of argument, let's assume that they both go from 0 to 1, and then our total fitness function is just the volume score times the area score. And now we want to turn this back, store this back into the geometry, and we want to do this for each box. So let's create this name dynamically, which has to be the iteration number, and the iteration number we'll just cheat, and we just get it from from outside of this. Could also just pull this directly from the detail, but this is a little bit easier. So then, just as we did before, detail, we get it from the count, it's the iteration, and it's gonna be 0, and because this is not the string, we don't need this. And now we are on the 9th iteration for this array, and our vex code is still not terribly happy, but it might be okay. Let's see what's going on there. I actually don't know what it's complaining about. Oh, it's complaining about the uninitialized variable, so let's maybe see if that really is the problem here. No, it's not. I'm actually not seeing the problem here. I don't know why it doesn't like this. Oh, because I can't spell. There we go. Great. And now we want to store this back into the detail. So detail attribute on ourself with the name and the score. But now we actually have to figure out what the score is. So the idea here is we want to minimize the surface area, and for the sake of argument, let's just say that our target area is 4.84, and this sort of gives us a number that's always positive, and we can fit this, let's say, from 0 to 4, and if this number is 0, our score is maximized. So let's reverse this here. And similarly for the volume, we know that we are aiming for 1. So we do the same trick here, and then we take this also. The 0 will be the 1 score. And that is it. Now when we look at the end of the for loop, we'll see that they all have exactly the same score, which is 0.71, and we want to get that score to 1 as much as that is possible. So what do we have to do now? We somehow need to create these variations that we want. And I think I would like to use just some point jitter for this. We just randomly modify the points and move them. This is probably too much. If we reduce the scale to here, that seems about right. Perhaps the seed we can put to the frame number, and then since we can't directly control the randomness in the point jitter node, I would like to make sure that this is really random by creating an ID attribute. And for this I like to use a point wrangle again, which I like to make black. And the idea for this point wrangle, let's call this random ID, is that we just create this attribute and then just give it some random number, and using the nRandom function. nRandom is basically a random function that is not based on any deterministic input. So this will always give us a different random number. Great. So this is our initial input. And then the question is, how do we actually end up figuring out the fittest chromosomes, and how do we do crossover and mutation? So for the sake of argument, let's just do another point wrangle, also black, and we will just call this compute next generation. And this will take all of these. They're basically the same boxes over again. That is our placeholders that we will overwrite with our selection algorithm, and then we know that we want the scoring input because that's going to be determined which of the chromosomes we'll keep. But we also somehow want to output the actual results that we had. So let's just rename what we scored into something else, and Houdini makes this easy as well. We can just say box star and old star, and now all of these are renamed, and then we can actually put them together, and this is what we will output. And then outside of the solver we can select what we want to display. Great, so if we look at this, we'll now have the new boxes and the old boxes, but for this to work we will actually have to remove them over here, because we don't really want to have to deal with all the old stuff. So I think we can just say old star, which we don't have on that frame yet. And then we also want to kill those groups so we can create them back down there in the group rename. Alright. This should work, and in theory we should be able to already run this for one iteration. And then we should... Let's get out of the solver. And what do we see here? Now we actually see them populated, and the previous frame doesn't have data here. I don't understand why this doesn't have data. This doesn't have data. Oh, it's the detail attributes. Never mind. Okay, so this now may work, but we don't have the old ones in there, which we do have down here. Let's see what happens if we go to frame 3. Okay, so now we have the old ones which are empty, and then here they get removed, and then back here everything gets scored again, which we can see in the details. Alright, one thing I noticed is that the scores were all the same even though we put the point jitter in already. That's because we actually did not input it to the scoring function. That does not really help with testing fitness. So this should work now. So let's go back, and now we actually get to see different scores due to the points being jittered. And the real complication on how to do all the genetic algorithm is now going to be in this point wrangle. And I will try to keep this as simple as possible, and hopefully still allow you to follow along, but this may be a little bit complicated. So we need to know the number of chromosomes. We could get these via detail call, but I sort of just like to do this via parameters to this to the point wrangle. Easy enough. Let's pop this in. We hope you still have this saved. And there we go, 10 chromosomes. Then for genetic algorithms, there are two other attributes that are really important. This is crossover, which is how many genes when you pair two chromosomes will be exchanged. And then the other one is mutation, which is sort of just a random modification of genes. So let's get this in, crossover. It's going to be a float that we call crossover. And the mutation is going to be similar. Going to be another float. Let's populate those. I like crossover maybe somewhere around 0.4, and then mutation maybe at 10%. We have to play with that to see how it really works. And we really want to just keep the fittest numbers of chromosomes, so that's basically going to be the ones that scored the best. So we're going to be keeping the top half. But before we can do anything with that, we actually have to get the scores and let's figure out which scores are the highest. So we're going to be storing these in an array, and we know that we have them in the detail attributes as score. So then let's see how that looks like. Num chromosomes, and we know that we have to get it out of the detail attribute. So that's going to be the detail from our first input, and it's a very simple name, just the iteration. So this now should give us the these scores from the detail. And actually, you know, that is not a particularly useful name, so let's change this. Let's actually call this compute score, and then actually just change this to score, and then in here we're just going to be using the score as well. And Houdini provides this nice argument sorting functions, so we can sort the scores, and this basically gives us the indices of the scores from smallest to highest. So now we have the sorted scores. And it might actually be useful for us to keep track of what the maximum score was. So let's put this as a detail attribute onto ourselves. Let's say max score. And then in order to figure that out, we will have to go to the sorted scores and look at the last entry, which is going to be num chromosomes -1. And then we actually have to look up the score via this index entry. Sort of like so. And then we might also want to know what the index was for this. So let's do this. So actually, let's just copy this and just say max element. And then we don't need the score anymore, we just need the index. And that's that. And now we can see that the max element was 0 and the max score was 0.667. Let's just quickly look at this. If we look at the detail here, 667 was indeed the highest score, and that was in the element index 0. So that works. So now what we want to do is we are getting these 10 placeholder boxes for every single iteration because we're just using the input. And we then just want to copy the point information over because each point is essentially an individual gene, and we just change them randomly a little bit. And then we sort of hope that with this algorithm, the ones that score higher will be retained, and then slowly compute the shape that has the same volume but minimal surface area. So how do we want to do this? We want to look at the top scoring entries. So those are the ones that are the first half. Let's use keep there. And the complication now is that we actually have to do the indices differently because they are the sorted indices. So to get the highest scoring index, we need to look into our sorted scores, and we start at the end, and then we just subtract n. Great. And now of that entry, we actually want to know what points are responsible for that. So let's call these point ones, and we do this by expanding the point group from the first input geometry. And we know that we called these box. So this is now going to give us the actual point indices from the highest scoring entry. And now we want to combine this with the next two highest scoring ones to sort of create the chromosomes for the next generation. So we will do this in a similar fashion. We go from M to M like so. that basically gives us numbers 1 and 2, and then we also want to know what is the index for that, and that is sort of similar to what we had here before, but in this case we actually end up subtracting this m as well. Great. And now we also have to figure out what those points are. Remember, these are all sort of in a single object. And let's call this point 1. In a single object. So we have to get to them via these point groups that we have created. Basically the same as above, only we use the J. And now we want to store this in the points that we are getting on input, that we are getting on the 0 input. So a similar thing, only now we have to sort of enumerate these slightly differently. And that's a little bit more complicated. So basically the top scoring chromosomes will all get 2 new chromosomes made out of them. So that means we need to keep space for 2 for each n. And then we sort of count by the ones that we mix with. And since m goes from 1 to 2, we have to subtract 1 here. And this should give us the target points. Great. And now what we want to do is we want to iterate through all of these potential target points and then basically figure out what point should we give to that. So let's do it this way. K is 0 via the size of the number of points that are in there. This may change if we sort of decide to do a different number of subdivisions on the boxes. And by default, we will get the point from the highest scoring one. And we know what the index is. That is basically 0.1 at this position, because they're all the same boxes with all exactly the same numbering. But now, for a certain percentage of these, we actually want to cross over and take the value from the other chromosome, the next scoring one. And this is going to be our crossover probability. Again, the n random gives us a different random number each time we call it, and it doesn't depend on any of the point numbering. So then, now we want to take the point 2 here. And the interesting bit here is sometimes we also just want to randomly mutate these, get completely new values, which sort of injects, new variation into what we are doing. And for this, I think we just want to jitter the point. So let's, so nRandom actually knows how to generate a vector as well. And from 0 to 1, so let's point it from minus 0.5 to 0.5. But now we also have to scale this. And, I tested this a little bit before. This one seems to work well. And now we have figured out what the new point is going to be, so we can set it back on ourselves as point. And we know the index for this, which is going to be the target index, and the value is going to be right here. And if we got everything right, then this is basically everything that we need. But something isn't happy here. So let's fix that. Let's fix that. And it also doesn't like, oh, that's point. It's, I decided to do these in singular. I don't like this. So let's make them plural. And then hopefully this will make everything happy again. Crossover, it doesn't like either, even though we defined this. Float crossover, no idea what it doesn't like about that. Let's see if the error message tells us anything. undefined variable crossover. So maybe I misspelled something. Float crossover. Looks like this is the same one. Let's just pop it back in there and see if that's... Yeah, I don't know what I spelled incorrectly before. Still not happy though. Now it looks like it's stuck. And that probably means that I did something else wrong. This is not really going to work. That's pretty funny. Okay, now it actually looks happier. And if all of this worked, then we should actually... this may actually be all that we need. So let's take a look at this. Things are definitely changing there. But we don't know if they're changing for the better. So let's do one more thing. We actually want to isolate this. And we want to, you know, we had created these old groups. So if we just do old 0, then we get, you know, one of these, which ends up changing in interesting ways. But we actually want to get the one that was the highest scoring element. And we can do this by just going at the detail from the solver, and then we want what we had called max element. And that should do it. Let's look at this. Alright. Something is happening there. So one of the things I would like to do is, because these are all so randomly modified, let's actually smooth these out a little bit. You'll still get the random number, but you know, at least the primitives are just gonna be staying at the same size. So let's maybe reduce this to 4, filter quality to 3, and then let's take another look at this and see if this sort of makes it any better. Alright. Something is happening there. But I'm not sure if the right thing is happening, because we would like these scores to increase. I mean, it sort of does seem to move in interesting ways. Alright, let's dig into this some more. Total volume, total area. The scores are really not all that interesting, so let's maybe display the score as well, so that we get to see it. And we want the max score from the solver. And display this, which is a very long number, not very helpful. Let's merge this though. And then perhaps let's just turn this into an integer. And then we may not be getting everything that we want, but we'll get a sense of the score. And now we may have to move this to the side. Let's move it there. And this is difficult to see. I like my background actually dark. Probably don't need this anymore either. And then let's see if anything happens here for us. The score certainly does not seem to be changing. So I suspect something may not be got quite right in our algorithm. So let's dive in the solver and let's figure out what's going on there. So first of all, I actually want to delete all the scores that we accumulated before. just to make sure that we are starting from a clean slate. All right, let's get rid of all of those. And now everything is 0. So let's look at this again. Ha, I see what's going on here. This was on points. This needs to run over the detail. And now we are getting a score. And at the end, we are getting a score for everything. That's great. I think there's one more problem here. The smoothing is just way too strong. I just want to smooth it out a little bit. Okay, so let's try this again. Let's reset the score. 66. And now let's run it and see if we are slowly making progress towards turning this box into a sphere. Now we can see that for each generation, the score slightly improves. We can also see that the surface area here is slowly reducing, and we can see that the volume ends up staying around 1, which is our goal. Actually change the shading to flat shaded. I like this much better. This looks pretty good to me. Sort of look at this compared to where it started out. But there's maybe one more thing we can do is we can actually, let's actually throw in a sphere. And let's make this a mesh. That seems fine to me, but now we actually want to get to something that has the right volume, which should be 1. So let's see what we can do here. All right, close enough. So if we look at this, this does not quite look right, but here we can see how it's actually approaching it. The sphere, the volume is not quite there yet, which is probably why the score isn't 1. So we can run this some more. But I think this is a pretty good start. There's maybe one more thing that we can do. We had configured the chromosomes, so we can actually up this to maybe 40. And now when we look at this, we'll see that we have 40 scores here now. So let's run this one more time with 40 chromosomes. This is pretty slow. I don't quite know why this is so slow. It should be much faster. There may be something else to dig into. All right, I think this was definitely too many chromosomes. So let's drop this back down to maybe 25. And I think there may be one more thing going on, and that is in the solver. If we sort of look at our point jitter, this can be a little bit more aggressive. So let's try this one more time. And see if this works any better. Still pretty slow. I suspect that there may be something not quite right in the solver. It should be running much, much faster. And it's the same problem again. This just runs once over the detail and not over all of the points. So now let's see if this is finally running at the right speed and converging to a better solution. All right, this is totally different, running much, much faster. And now you can also see how it's slowly starting to approach the sphere here. There's one more thing that we can do. We can actually give it a little bit more space to run, maybe 2000 frames. And now we can see how the genetic search algorithm starts approaching the sphere. by really only having a super simple target function, which is trying to keep the volume at 1 while trying to reduce the surface area, which, as you can tell, for the sphere is 4.87, and I cheated in the solver because I know that the theoretical result should be 4.84. But there are other ways in which these target functions can be constructed to motivate the right behavior here. But I think this is pretty good. Yeah, this is very close to a sphere. We could try to give it more subdivisions now. Could maybe give it this many. So now we have basically almost 300 genes per chromosome. And then the other thing we can do is in the solver, there's sort of some parameters that we control here. Perhaps we want to keep a little bit more of the fittest solution. And then let's give this one more quick run. And let's see what happens. Taking a bit longer now because there are more points that get modified, and we sort of have to get the randomness right for every single point moving towards the direction of a sphere. But we can see again how sort of surface area keeps decreasing and the total volume is trying to get back up to 1. And I suppose if you ever wanted to create a sphere with almost perfectly sized quadrilateral primitives, this could be one way of doing that. Alright, I think this is pretty good. And now the whole point of this exercise was to see if we can do this much more efficiently in PDG. And then clearly there's sort of more interesting problems to which the genetic algorithms can be applied. But I think this is a pretty good example. I think this is good enough for now. So you got an introduction to genetic algorithms, and I showed how to implement them in SOPs. And this concludes part 1. And then for part 2, I will show how to do all of this also in PDG. And perhaps we can find a better example, but we'll start with a box to a sphere first. See you soon.